So hello everyone, welcome for this session of Quantum Space-Time Seminar. Today we are very happy to have SoumyadeepChaudhuri from Hebrew University, and he's going to tell us about symmetry, non-restoration in large and huge theories. Over to you, Soumyadeep.
Yeah, thanks. Thanks for inviting me to give a talk. So my talk would be based on two papers. One which we wrote last November. This was in collaboration. The work was done in collaboration with Chang-Ha Choi, who is a graduate student at Stony Brook, and Eliezer Rabinovici, who is a faculty member at Hebrew University. And the second work appeared recently, in just about a month ago, and this was done in collaboration with Eliezer again. Okay, so yeah. Okay, so just give me 1 second. Okay, for some reason. Okay, yeah. Okay, so I'm going to talk about spontaneous symmetry breaking of theories at high temperature. Spontaneous symmetry breaking, but by that I mean spontaneous breaking of global symmetries, which plays a very important role in characterizing or classifying different phases of systems.
Which are the one?
And a commonly held belief is that such spontaneous breaking of global symmetries is actually a low temperature phenomenon. That is, if such a symmetry is broken at low temperatures and they are restored once you raise the temperature sufficiently. And familiar examples of such symmetry restoration is for instance, the demagnetization of magnets above the Curie temperature, or the melting of solids. In this case, in the first case, you have a rotational symmetry which is broken, and once you heat the temperature heat this magnet sufficiently, the rotational symmetry is restored. And similarly, in case of melting of solids, you have both translational and rotational symmetry, which is broken in the solid. Then you have a specific crystal structure. Once you heat the system sufficiently, it melts, and these symmetries are restored. So there are actually interesting systems where a symmetry that is broken at that is unbroken at low temperatures is actually broken at a critical temperature, at a non-zero critical temperature. And this phenomenon is called inverse symmetry breaking. And common examples of such inverse symmetry breaking are these things that I have written here. Rochelle salt, which is potassium sodium tartrate, and certain liquid crystals show this kind of a behavior, where a symmetry in the system is actually broken at a non-zero critical temperature. But in all these cases, this broken symmetry is restored eventually as the temperature is increased. So the abundance of such kind of symmetry restoration in nature raises the question if such a behavior is universal. That is, if a symmetry is broken at some low temperature, whether it would be restored in all such quantum systems.
Sorry, so can I just ask one thing about this previous slide of yours?
Yeah.
Since the notion of sort of symmetries and so on is not a duality invariant notion, no? I'll tell you where I'm coming from. If you take the two-dimensional Ising model, yes, right, it has a duality between high temperatures and low temperatures, which exchanges the order and disorder variables. So, you know, the high temperature behavior in terms of the disorder variable is equivalent to the low temperature in terms of order and so on. And if you have symmetry breaking at low temperatures in one variable, you have it at high temperatures in the other. So all I'm saying is, in a sense, I mean, your question is well defined. If there is a symmetry broken vis-a-vis some notion of order at low temperatures, is it restored at high temperatures? But, yes, you know, sometimes after a change of duality, it could look the other way around, which is towards your point in between.
Yeah,
Yes.
but is there some concrete example of such kind of symmetry breaking that one observes due to such dual structure of theory? I mean, there's a question.
Canonical example, two-dimensional Ising model, right? Z2 symmetry.
Yeah.
That's the example.
But even in that case, you don't have a symmetry broken phase at high temperature, right? First
You
of all,
do in terms of the disorder variable, right? You exchange the under the duality at low temperatures. You would break the order symmetry, the Z2.
So you're talking about higher form symmetries, I guess, right?
Just the spin variable.
Yeah.
You have to spin at every site, and the variable is the spin operator.
Yeah.
Then at high temperatures, you go to the corresponding dual variable, which is non-local.
Yeah, that's what I'm saying.
It's non-local.
So you're talking...
No, it's anyway, you should go on. It's only non-local vis-a-vis the earlier variable, but it's a totally local variable in its own right. See, the order and disorder variables have a non-trivial, OPE, etc., which doesn't preserve locality, but each of them is a perfectly good local variable in its own right. No. Okay, anyway, go ahead.
But Sandeep, the question of whether the ground state is invariant under a given symmetry or not is an invariant question, right?
It is an invariant
independent of the language.
So I'm talking, but I'm not talking about the ground state.
Unless you have two symmetries, and then you are talking about which symmetry is broken.
Yeah. No, as I said, his question is well posed. Let's say there is a symmetry, and let's say at low temperatures, okay, if he doesn't want to say ground, so low temperatures it is broken. Is it restored at high temperatures? Right? That's a perfectly good question. All I'm saying is that there are situations where you have a duality between high and low temperatures, and so you will have an inverse situation where there's a just by the duality map where something is broken at high temperatures and restored at low temperatures, which is what he was saying in the middle. And I was just trying to say that it can happen just as a consequence of dualities in systems. Anyway, it's a side comment. Go ahead, please.
Yeah, but okay. So I'll try to address this but okay. So as I was saying, the universality of such symmetry restoration was actually challenged by Weinberg in a 1974 paper, where he was considered a 4-dimensional ON cross ON symmetric vector model. And in certain parameter regimes, one of the ON groups in this model remains broken up to very high temperatures. And the theory, but nothing conclusive could be said about symmetry restoration beyond a temperature scale, because this theory is UV incomplete. The theory that Weinberg had considered, that was UV incomplete. And one actually hits a Landau pole in this case. And what one can show is that up to the Landau pole, the symmetry remains broken. One of the ON group remains broken up to the scale defined by the Landau pole. Okay, so, and many other works actually subsequently suffer from similar limitations. So one cannot ask questions about arbitrarily high temperatures in these cases.
Sorry, in Weinberg's model was the matter and the bifundamental of the two ONs?
No, they were in the vector, the fundamental representation. There were two scalar fields.
One in the fundamental of the first ON, one in the fundamental of the second ON, and they're interacting with each other somehow?
They're interacting with each other, yes.
I see. So this is a solvable model, I suppose.
Yeah.
Okay, thank you.
So
how are they interacting? Because
so you
phi
have
1 square, phi 2 square.
Phi 1 square, phi 2 square, these kind of interactions. So we considered a similar, recently last year, we found an example of a model in fractional dimensions, which demonstrates symmetry non-restoration. And this model was actually quite similar to the model that Weinberg had considered, except that the symmetry group in this case was ON1 cross ON2. And again, we had these scalar fields transforming in the fundamental representations of these orthogonal groups. And we considered Wilson-Fisher-like fixed points for these models. And the advantage of considering CFTs is that they don't have any intrinsic scale in them. And hence, if a symmetry is broken at any non-zero temperature, it remains broken at all temperatures, because there's nothing to demarcate low temperatures from high temperatures. So it's a so this was studied last year, and we found that that such a symmetry breaking indeed happens in these regimes when n1 and n2 are much greater than 1, and when the dimension is between 3 and 4, and when the ranks are unequal, that is when n1 and n2 are not equal, then the ON symmetry corresponding to the smaller group actually gets broken at any non-zero temperature.
And does this continue to work in 3 dimensions?
No, I mean there are some problems in extending this to 3 dimensions.
But
and
you can solve the model, and you don't need the epsilon expansion to solve the model, right? You can solve it just at large n.
In the large n limit, you're saying.
And so you can answer that, and the answer is that
in the large n limit, you're talking about the n tending to infinity limit.
Yeah.
Yes. So you hit some singularities once you take the dimension to 3. So that's the problem.
Yeah, thank you.
And sorry, Soumyadeep,
Yeah.
you said, so if I understand, when you said it's a CFT, this is in how many dimensions?
In 4 minus epsilon dimensions.
Oh, for all epsilon, is it?
It's for epsilon for lying in the interval 0 to 1.
I see. And is it true for epsilon equal to 1? No, huh?
No, that's the question that Shiraz was asking. So, but when you try to take epsilon to 1, exactly equal to 1,
yeah,
then you hit certain singularities in the large n limit.
So it's not a CFT. It's not a CFT anymore.
No, it's a CFT. It's a CFT, but this result doesn't hold.
Okay,
but the result that regarding the symmetry non-restoration,
I understand.
That doesn't hold.
I understand, but can you argue that it continues to be a conformal field theory?
So you can solve the beta functions, find the roots of the beta functions in this case. The beta function is in the large n limit, the beta function is exact.
And it vanishes.
You can find and then you can try to find the roots of the beta function.
And you can organize it so that it's a conformal field theory for 3 dimensions also.
Yes, but the problem is that in that case, this ordered phase doesn't persist in that case. Okay. That's the problem.
Okay, I understand. I'm trying to understand if it was.
And this result was actually found even for finite. So what happened was that in the large n limit, in the n tending to infinity limit, that is when n1 and n2 both are taken to infinity, you have a conformal manifold. Mm-hmm. And when you take 1 over n corrections, the conformal manifold is lifted. And when n1 and n2 are not equal, then what happens is that the CFT that survives under 1 over n corrections, that actually shows symmetry non-restoration. So this result, for the fractional dimensional model, one can actually generalize this result to finite n as well. So finite but large n. Okay.
Sorry, Soumyadeep. And just to understand, I mean, the way I would do this calculation is to compute the quantum effective action as a function of phi1 squared and phi2 squared and check where the minimum is. Is that what you did?
Yes. Yes.
Okay, thank you.
Yeah.
Yeah. So just to continue on Shiraz's questions, I will do that. And then you were saying that the solution of this equation will presumably give a real value for the condensate for the N2 field.
Yes.
But complex values for the N1 fields, is that the reason why?
That remains unbroken. I mean, that symmetry remains unbroken.
So what does it mean? What does it mean? The condensate for the N1, it does not have a solution, meaning it has complex solution or something like that, or what?
No, it's 0.
0.
Oh, as soon as you make N1 greater than N2, so the N1 condensate comes to be 0. I see. Oh, wow.
Yes. So the minimum is along a particular direction, which is that of the field corresponding to the smaller, which transforms in the fundamental representation.
It remains 0 at any temperature. I see.
Yeah. So since we are working with the CFT, the results are true for any non-zero temperature.
And both of them would be 0, right? Phi1 square and Phi2 square. At the minimum, Phi1 square and Phi2 square would both be 0. Is this right?
No, if that is true, then both the symmetries would be unbroken.
Yes.
Right.
But I'm saying that at finite temperature, what happens is that in the one of you have a condensate for one of the ON groups. So
right. I was asking in D equals 3. In D equals 3, both become.
So in D equals 3, okay. So in D equals 3, what happens is that this condensate goes to infinity. I mean, the value of phi goes to infinity.
So it becomes sick. The vacuum stops existing. So.
Yeah.
I mean, the theory is not well defined.
Yeah.
Oh, so I see. So it's not like there's a well-defined CFT, and then you're asking, it's just a sick theory, huh? For
in D equal to 3. Yeah.
Equals 3. Okay, I see.
So interesting. So the quantum effective action at 0 temperature looks okay, but it's only at finite temperature that it goes up to infinity. Is this what you're saying?
Yeah.
Okay, we'll come back to this.
So I think I have to remember this is I have to remember the details of the results. But yeah, so for finite temperature, this is what we found, that I remember distinctly, that this condensate just becomes infinite, just blows up. So this is the problem for taking this. But but this is also consistent with the statement of this Mermin-Wagner theorem. It says that in 2+1D at finite temperature, you cannot have a continuous symmetry which is broken. So this is a manifestation of that. Okay. In a local theory, in a local quantum field theory, at finite temperature in 2+1D, you can't have the spontaneous breaking of a continuous symmetry. Sure. So it's a manifestation of that. However, one can ask what happens when say when you take the limit that n2 equal to 1, that is, you take it to be z2. We tried to explore it, but we did.
So I'm sorry to interrupt so much right at the beginning of your talk. Yeah. But you know what you said about Mermin-Wagner theorem, you can just say about just ON sigma model, one field. Right?
Yeah.
Now, one field ON sigma model doesn't have some runaway behavior at infinity at finite temperature.
Yeah.
So that runaway behavior at finite temperature is not by itself a consequence of Mermin-Wagner theorem.
No. But I'm saying that runaway behavior, there should be something, some problem in extending this to.
I mean, the way it works in the one field ON model, sigma model is that the phase transition temperature just goes off to infinity. Anyway, we can talk about this.
Yeah. I mean, the wave can just be 0, right?
Right, exactly.
Yeah. So, right. Okay, so my talk will actually be on some 3+1 dimensional large N gauge theories, which demonstrate symmetry non-distortion in the n tending to infinity. I would like to mention at the very outset that the results for finite n are not conclusive actually in these models. But okay, so I will first consider Banks-Zaks like fixed points for these theories, and an important feature of these theories in the planar limit, that is when n tends to infinity, is that there is a circle of fixed points in the space of couplings.
Sorry, can I ask one question just to understand what is a CFT with a spontaneous symmetry breaking? So this is happening at finite temperature.
Yes.
But does this mean that if I do an OP, let's say, which I can do even at finite temperature, I see not a unique vacuum state. I mean, not an identity operator, but somehow a multiplet of identity operators. How should I think of the spectrum of operators?
You would get multiple vacua. That's true. You will get multiple thermal vacua corresponding.
So even using state operator map also, now I should get multiple identity type operators.
That I have to.
Or is not
because you're explicitly breaking the. I'm trying to understand whether the state operator correspondence would work when.
Because the conformal symmetry is also broken, right?
Yeah, that's what I'm saying. The conformal symmetry is broken, and hence the state operator correspondence is itself somewhat suspect. I have to think
about so one should not think of this as a, the theory does not have conformal symmetry there, right? I mean,
the theory has conformal symmetry, but I'm putting it at finite temperature. So I'm taking a conformal field theory and putting it at finite temperature.
No, but even if you do that, you could have done the OPE. But I'm saying,
Yes.
moreover, because of the way over the phi, the conformal symmetry itself is broken spontaneously.
Not spontaneously. I'm explicitly breaking it when I'm putting it at finite temperature. I'm explicitly breaking the scale invariance, right? So there is a scale now in the problem.
No, but when you put a CFT at a finite temperature,
yes,
the CFT that does not have this kind of feature, right, where the symmetry is not broken, any symmetry.
Oh, you are talking about the ground state, whether this is broken at 0 temperature.
No, I'm just thinking finite temperature.
Yeah.
Okay, I can still do the OP, right? The operator product expansion
yes.
I can still do. So I'm saying, is it something that I can do here?
Abhijit is talking about the theory on R2 times S1. That's how he's thinking of finite temperature. Is this right, Abhijit?
Yes.
And then then you're talking about the operator insertion on the manifold R2 times S1. Identity operator insertion.
Yes,
that's right. Yeah.
Yes. So can I do the operator product expansion? And if I do that, then what do I see in the expansion? And what is there a signature of this vacuum being not invariant under the symmetry?
So okay, so I need to think about it, but you would get distinct thermal vacua. In this case, you would get distinct thermal vacua which give you the non-equivalent states. So if a symmetry is broken at a finite temperature, you will get distinct thermal vacua for that. I need to understand how it manifests in an operator product expansion at finite temperature.
Okay.
But yeah.
Okay. Thank you.
Okay. So an important feature of these theories in the planar limit, that is in the intending to infinity limit, is that there is a circle of fixed points as in the space of couplings. So this is quite surprising actually, because this theory is a non-supersymmetric theory. So a conformal manifold such as this is something that one would usually get in supersymmetric theory. But in this case, we were able to show that one gets a conformal manifold of this form at all orders in the 't Hooft expansion, in the expansion of 't Hooft couplings in the intending to infinity limit. Okay, so and for finite n, we don't have for finite n, we have done some computations, but it's not conclusive as yet. Whether this conformal manifold survives or not. Okay, so and in certain parameter regimes, I would argue that a subset of points on this fixed circle demonstrates spontaneous breaking of a global symmetry at all non-zero temperatures. And this is what I would mean by thermal order. That is, the CFT has a thermal order, the CFT demonstrates thermal order. This is what I would mean by that. And I would also show that the spontaneous symmetry breaking is accompanied by the Higgsing of a subset of the gauge bosons in the theory. Okay. So I will then consider marginally relevant deformations of these fixed points. And these deformations will be obtained by varying certain quartic couplings between the scalar fields in the model. And in the intending to infinity limit, the RG flows triggered by these deformations approach the points in the fixed circle in the UV regime. And in the IR, they approach a unique weakly coupled fixed point, which lacks the thermal order that I mentioned earlier. And therefore, for a subset of systems defined by these RG flows, we'll have a transition from a disordered phase at low temperatures to an ordered phase at high temperatures. And using thermal perturbation theory, I will give an estimate of the corresponding critical temperature. Okay. Is there any question at this point? Because I'm going to enter into the description of the model. This is the introduction.
So the matter content, etc., you're going to
I'm going to talk about it, right? Okay, so let me now describe the models. And the gauge groups in these models have this structure where you have GI cross GI. You have two sectors.
Sorry, Soumyadeep, before you start on this, just about Abhijit's question. Abhijit, I would have thought that since OP was some short distance thing, it didn't depend on the vacuum. So it would continue to hold. It's just that some of the operators that appear on the RHS would have non-zero one-point functions.
I think that is true. That's how you do it in
No, but the 1-point function you anyway have for a thermal
for a thermal operator. So nothing dramatic appears to. Yeah.
I see. There should be some signature at short distances or not? No.
Well, actually, exactly in the 2+1 dimensional theory, you never will have the spontaneous symmetry breaking, right? Because of Goldstone.
Right. But in this epsilon.
Yeah, that probably is. I would have to think.
Okay. No, but okay. That's what I would guess.
You are still thinking about this 2+1 dimension. Is that so? I mean, that's what. Okay. Okay.
So my question was more general, but yeah.
Yeah. Okay. Right. So the gauge groups in these models have this structure where you have two sectors, and in each sector, the gauge group is of this form: GI cross GI, where you have where GI can be either SONCI or SUNCI, and the ranks NC1 and NC2 can be unequal. So the model where GI is SONCI, I'll call it the real double bifundamental model, and the one where GI is SUNCI, I'll call the complex double bifundamental model. The reason for coining these names will become clear in a moment. Okay, so the matter content in each sector comprises of two sets of massless fermions, and each of these fermions transforms in the fundamental representation of one of the GIs and is invariant under the other. So, so I'm denoting these fermionic fields by massless fermions by psi I and chi I, where P denotes the flavor index, which runs from 1 to NFI. And in addition to these fermions, there's a massless scalar field, which transform NCI cross NCI matrix of massless scalar fields, which transforms in the bifundamental representation of GI cross GI.
Soumyadeep, why does your gauge group have the index I?
So there are two sectors, as I mentioned. So there are two sectors, and in each sector, so in each sector, the gauge group is GI cross GI, and then there are two such sectors, and the ranks can be unequal. NC1 and NC2 can be unequal. So right, so in case of the real double bifundamental model, the fermions, the massless fermions are Majorana fermions, and in case of and the scalars are real scalars, and in case of the complex double bifundamental model, the fermions are Dirac fermions and the scalars are complex. So this is the reason for coining these names. Basically, they are named after the scalar fields, the way the scalar fields behave in these models.
Sorry, and to understand, Soumyadeep, if your fermions, for instance, are fundamental, a fermion that's fundamental in the first component of G1 is also fundamental in the first component of G2.
No, so the fields in each sector are invariant under the gauge group in the other sector.
Oh, I see. So even the fields have an I component. Thank you.
Yeah.
So there's one field that's fundamental under. So there are, sorry, just to totally understand, let's say they were all SUs.
So I'll show a previous structure that would probably, a figure would probably clarify it.
Yeah.
So the scalar fields, in the next slide, there's fields interact with each other via both single trace and double trace quartic interactions. And a double trace quartic interaction couples the scalar fields in the two sectors. So this is a schematic diagram of these fields. So the phi1 transforms under the bifundamental representation of GI cross GI. Here, phi1 transforms under, say, SONC1 cross SONC1. And the fermionic fields, they transform in the fundamental representation of this SONC1, say. And then there is a flavor index, which is NFI. There are two such fermions, psi I and chi I, which transform in under one of the SONCIs and is invariant under the other. And this sector, all the matter fields here are invariant under the gauge transformations in the other sector. Okay, and this dashed line just indicates that these two scalar fields are coupled to each other by some interactions, and this zeta is a coupling which would appear later. But this shows that these two scalar fields, these two sectors are coupled only via an interaction between the scalar fields in the model. Okay.
And this is in 4 dimensions and SUN gauge, and the gauge, all the
gauge group can be SON or SUN.
Fine.
And depending on that, I mean, one is this real double bifundamental model.
Fine. And this in 4 dimensions. We are in 4 dimensions.
4 dimensions.
Okay.
Yes.
Thank you.
So to tame the UV divergences, we work with dimensional regularization and the MS bar scheme. And the renormalized Lagrangian has this form. The first few terms are just the usual kinetic terms. I mean, this term is the term corresponding to the field strength of the gauge fields. And these are the usual covariant derivative terms for the fermionic fields and the scalar fields. The interesting terms are given in the last 2 lines. So the first term here is a single trace quartic interaction between the scalar fields in the ith sector. The second term is similarly a double trace quartic interaction between the scalar fields again in the ith sector. And this last term is a double trace interaction again, but it couples the scalar fields in the 2 sectors. So we have basically 5 couplings. There are 2 HI tildes which correspond to single trace interactions. There are 2 double trace quartic interactions, and in each sector, and then there is another coupling zeta tilde, which is the double trace quartic interaction which couples the scalars in the 2 sectors. And there are the gauge couplings, which I'll come to in a moment. So here kappa is half for the real double bifundamental model, and kappa is 1 for the complex double bifundamental model. Okay, and Fi alphas are the field strengths corresponding to Vi alpha. The gauge fields have 2 indices, one which the index I denotes the sector to which it belongs, and alpha distinguishes the 2 GIs in each sector. Okay. And the gauge couplings corresponding to the 2 GIs in each sector is the same. And this I'm calling GIs, small GI. And this statement is actually invariant under the Aji flows. That is, if you choose them to be equal, that for the 2 GIs in each sector, if you choose the couplings to be the same, they remain the same under Aji flow, and that can be argued from an exchange symmetry. That is, if you take phi I to phi I dagger and exchange psi I and chi I, and similarly transform these gauge fields as well appropriately, you would be able to show that this Lagrangian remains invariant, and that ensures that the gauge couplings corresponding to the 2 GIs in the ith sector are the same. If you choose them to be the same at 1 energy scale, they would remain the same at all energy scales.
And you also have to choose the HI tildes and FI tildes to be the same?
No, I'm just saying that the GI, there are 2 GIs in each sector, right?
Can you just show that diagram? Just show that diagram once more, right?
Oh,
Thank you. So in each sector, if I understand, you actually have NC1. Wait, let me get this right. You have 2 gauge groups, right? NC1 and NC2.
Yes.
Huh?
In each sector, I have just two gauge groups with the same rank, SONC1 cross SONC1 set. And I'm just saying that the G1, the gauge coupling corresponding to these 2 SONC1s are the same.
And those gauge coupling, Soumyadeep, if I understand, they don't have to be the same as those for the NC2s. Is that correct?
No.
Right? Okay. Yeah. Okay, I understand. And if I may, can I ask one more thing, since you're showing this diagram? That Lagrangian you wrote down, it presumably preserves your NF1. You have now actually 2 flavor symmetries in each sector. No, if you just show that diagram, NF1 cross NF1 rotating the psi1 and chi1, and also NF2 and NF2 prime, if you like, right?
Yeah.
And that Lagrangian of yours preserves all these symmetries.
These are not symmetries, but
flavor symmetries.
Yeah, Yeah. So this is just a trace. You can write it as a trace of, you can express these fermions as basically matrices, but
Right,
with
right.
NCI cross NFI matrices. And then this is a trace of chi bar d slash chi.
Yes. So I think it preserves these symmetries too, or am I wrong about it? Flavor symmetry.
Yeah, I mean, okay, so the flavor symmetry, what is the transformation? You are talking about UNFI, something like UNFI, right?
Yes.
So yeah, so this would just introduce a U. This was so if you have something like chi bar d slash chi, right? And this would just transform this by and you are say the transformation is something like chi goes to chi u, something like that, right?
Correct. So it
So you will have u dagger, trace of u dagger chi bar d slash chi u,
yes.
and by the cyclicity of the trace, this u dagger and u would cancel them.
That's right. That's what I would expect. And then, is this the most general Lagrangian in its form that preserves your gauge symmetries and all your flavor
So
symmetries?
you can have Yukawa interaction.
I see, which would preserve all the symmetries.
Those would break chiral symmetry.
Those would break. And so what would be an example of that? If you can just show that diagram again, or just say in words.
Yeah, you can have something like, say, psi bar, phi, chi, something like that.
Psi bar. So phi chi, huh? Psi bar phi chi. But wouldn't that break that has one psi and one chi, and you have two independent flavor symmetries for the psi and chi, no? If I understand.
Okay, so you're saying that the flavor, you want to preserve the flavor symmetry for individual for each.
I'm just trying to understand.
Yeah, so that would rule out the if you demand that would rule out such kind of so that would rule out this, but it's completely consistent with the gauge symmetry.
No, sure. But so if I take the flavor symmetries also into account, you're starting with the most general Lagrangian.
Yeah.
And then imposing these extra conditions on the gauge couplings, huh?
Yeah.
Okay, thank you.
Yeah.
These conditions on the gauge coupling, you can justify them saying that the model has Z2 times Z2 symmetry, right? So if you go to the diagram,
there's a Z2 symmetry. Yeah.
If you go to the diagram, there is a flip
Yeah.
symmetry on one side,
Oh, I
another
see.
flip symmetry on the other
Okay,
side.
good.
So that's what I was saying.
So once you take that into account, the last assumption is justified.
Oh, I see. So then if you impose all of these symmetries, you're writing down the most general Lagrangian.
Most general, yeah.
Huh? So at least it should be the form of the Lagrangian you might expect is preserved in the RG or something, but then you actually have fixed points.
Yeah.
Okay.
So the couplings would have RG flows, but then I'm going to take the fixed points. Consider the fixed points.
Yes. Okay. Thank you.
So I'm going to work in the Veneziano limit, where the ranks of the gauge groups are taken to infinity, while the ratio of the number of flavors and the rank in the ith sector is taken to be a finite number xfi, and the ratio of the two ranks that approaches again a finite number r. And in this limit, the couplings would scale in this way. So basically, the GI square, the gauge couplings scale as 1 over NCI, and HI tilde, the single trace couplings scale as 1 over NCI, whereas the double trace couplings, they scale as 1 over NCI, or 1 over N square.
Sorry, Soumyadeep, you could also have further restricted your model to have symmetry on the left-right flip. But you won't want to do that, right?
No. I want to keep them so that you want to set NC1 and NC2 equal or something like that. Is that what
right? Just put everything same on left and right.
No,
and then
but that's not what I'm interested in. Yeah.
Okay. Thank you.
Okay, so the global symmetries of interest in the real double bifundamental models. I'm using this abbreviation RDB and CDB for these models. So the global symmetry of interest is this, where the scalar fields and fermions and the gauge fields, they transform in this way. So the gauge field Vi2 remains invariant, whereas I've just shown that the terms that the fields that transform, and left out the fields that don't transform. That is chi and Vi2, they are invariant under the transformation. So I'm considering a transformation of this form, where Ti is an NCI cross NCI diagonal matrix of the following form, of this form, where the first element is -1 and all the other diagonal entries are 1. And the effect is basically to flip the sign of the first row in phi I, and similarly the first row of psi, if you think of psi as a matrix, and the first row and first column of Vi1. So these are the only transformations. And similarly, the global symmetries of interest in the complex double bifundamental model are exactly analogous, but this matrix is, instead of -1, 1, 1, 1, you have an e to the power I theta. The theta can vary from 0 to 2 pi. So what one can show is that, yeah, sorry.
Sorry, I'm a bit confused. Sorry, the global symmetry that you're talking about here seems like a subgroup of the gauge symmetry.
No, it's not.
It's not SU.
It's not. It's not, because there's first of all an order parameter, gauge invariant order parameter, which is this determinant of phi I. So for instance, you can consider determinant of phi I, which would be invariant under a gauge transformation.
Oh, it is not U, you mean? Right.
Yeah,
it is not U.
It's not
It
U.
is the overall
So
U1 is there.
I'm considering,
right,
special orthogonal or special unitary groups.
The baryonic symmetry, right? Yeah.
It's a baryonic symmetry, yes. So one can one can consider, one can show that each of these transformations maps one set of gauge equivalent configurations to another. And the order parameter for this symmetry is the expectation value of determinant of phi I. And the order, so since the order parameters are expectation values of baryonic operators, I'm going to call these symmetries baryon symmetries in the models. So for each sector, there are 2 baryon symmetries. Okay. So sorry, for each sector, there is 1 baryon symmetry. So you have 2 such baryon symmetries corresponding to the 2 sectors in each of these models. So I'm going to employ perturbation theory to determine whether the baryon symmetries are broken in thermal states.
Sorry, I'm a bit confused. Why not 2? Let's say case of SU, let's say, why there, I mean, it seems that there are 2 U1s for both the gauge groups, right? So you are looking at only one of them, because why?
Sorry, the scalar field actually transforms under both of them. So what exactly do you? So are you saying that I could have chosen, instead of flipping the sign of the first row, I could have flipped the sign of the first column?
No. Let's say in the second case, for the SU case, you have 2 U1 symmetries, but for one for each sector, right? Why not 2 for each sector?
They are related by exchange, this exchange symmetry that I talked about, I put the, so there's an exchange symmetry. That's true. There's an exchange.
So there are 2 U1s.
Yeah,
so
there are 2 U1s, but this exchange symmetry is I've already talked about this exchange symmetry, which leads to choosing these 2 gauge couplings. So you can just flip the rows and by columns of phi I here, right?
Yes.
Instead of flipping the rows, you can flip the columns and so on. And instead of psi I, you can take chi I.
Okay.
Instead of Vi1, you can take Vi2. That's true.
Okay, so okay, good.
So
there are 2
considering
U1s.
one of them. Yeah.
So overall, there are 4 U1 symmetries.
But yeah. So
and Abhijit's 4 U1s are partly broken down also by the scalar potentials, right?
Yeah.
So what the scalar potential breaks these 4 U1s to what, please?
Yeah. Sorry, the scalar potential.
You have some potentials for phi's, right?
Yeah.
That partly breaks down these 4 U1s to some subgroup.
No, it doesn't break.
It doesn't?
Why does it break? It doesn't break. Phi dagger, right?
Yeah. I also did not see why it works.
Oh, it's phi dagger. Okay, thank you.
Soumyadeep, I'm very sorry. Show that diagram that moves like whatever diagram once more, if you don't mind. It'll just make sure I understand. So now your U1 pertains to the U1 part of the NC1, the 2 NC1s and the 2 NC2s, right? If I understand.
Okay, so I'm just transforming one of the rows by e to, I'm just multiplying one of the rows by e to the power I.
Yeah,
so phi is a matrix.
Sorry, same question. Why are you calling it a Z2 if it's a U1? I suppose that's what I must.
Which
No,
one
no,
is
Z2 is
Z2?
the SO case.
Z2 for the SO case, and
Ah.
U1 is for the SU case.
Sorry.
Yeah.
Okay, yeah, let's just do the SU case if you don't
Yeah.
mind. So
Yeah.
I could think of it as the U1 subgroup, which is, the whole group could be UNC1 cross UNC1. Then I think you're gauging the SUNC1 cross SUNC1 subgroup, and that leaves the UNC1 cross UNC1.
Yeah.
Right?
Yeah.
Is that correct? Huh?
Yeah.
Okay. Thank you. Thank you.
Sorry, you had this exchange with Abhijit, which I didn't understand, but the reason that there's only one rather than two is because you're imposing a up-down flip symmetry.
Yeah, there are two. There are two such things, but one can consider either one of them. It's
You
fine.
can consider either one, and were you studying only those Lagrangians that maintain the Z2 flip symmetry between up and down?
Yeah.
And therefore,
because I'm setting these couplings to be the same, right? G1, the GIs to be the same in the two.
Yeah, thank you.
No, but the U1 symmetries are still two, right? The U1 symmetries themselves are still two. The Z2 is kind of an automorphism.
Yeah, there's still
same with the global symmetries, NF1 and NF1.
Yeah, no, absolutely right. But you can't, if you violate one, you have to violate the other.
Yeah, if you insist on Z2, that's right. So you might as well look at one.
Yeah. Okay, so I'm going to consider. I'm going to employ perturbation theory to determine whether these baryons symmetries are broken or not in thermal states. So here I would like to give a disclaimer that thermal perturbation theory is generally plagued by infrared problems which require resummation of certain diagrams, and this typically modifies the subleading terms in such expansions. And here I'm going to focus on leading order terms, and we expect the IR issues to not affect the results based on such leading order calculations. Okay, so at this leading order, the order parameter that I talked about, that is related to the thermal expectation value of the scalar fields as shown here. So basically, since I'm going to talk about weakly coupled theories, at leading order, the expectation value of this renormalized determinant would be equal to roughly equal to the determinant of the expectation value. And when phi I is equal to is non-zero, the expectation value of phi I is non-zero. This is not a gauge invariant quantity, phi I, the expectation value of phi I. But one can bring it to a diagonal form. I will show that it can be brought to a diagonal form with non-zero entries, and that would lead to the determinant being non-zero when phi I is non-zero, which in turn would mean in this weakly coupled regime that the expectation value that the order parameter, corresponding order parameter, is not zero. So this means that, is there a question?
Yeah, no, you should complete, please. But just to say, doesn't this mean that your SUNC is being broken down to basically the two product of SUNC cross SUNC is breaking down?
Yeah, so I said that there would be a Higgsing, right? There would be a Higgsing of the gauge bosons. I would talk about that. Yeah.
Okay, but probably just to the diagonal, right? Because you want the determinant to be non-zero.
Yeah, I'll talk about it.
Sorry.
So to determine whether phi I is non-zero, one can consider the thermal effective potential of the scalar fields. And up to leading order in perturbation theory, this potential has both quadratic and quartic terms. So the quartic terms are the ones that appear here in the Lagrangian. So one can take the negative of the terms that appear in the Lagrangian, and that gives the quartic term. And for the theory to have a stable vacuum, we need these quartic terms to be bounded from below. And this is indeed true, as we have checked for the fixed points that I'm going to talk about. And okay, so and the quadratic terms have this form where the quadratic terms are of this form: trace phi I dagger phi I, and the coefficient is m thermal I square, and this m thermal I square is a temperature dependent quantity. This was zero this is originally zero. This quadratic piece was originally zero because all the fields were massless in my Lagrangian. But once you introduce temperature into the picture, so that these scalar fields pick up thermal masses, and they receive contributions from these
sorry, Soumyadeep, you're going to compute the thermal effective potential for what again, please?
The scalar fields.
In a particular gauge, you said?
So these are gauge invariant quantities, right?
You're going to compute so for phi dagger phi, trace phi dagger phi? No?
Not trace phi dagger phi. There's a single trace quartic interaction as well.
No, you're going to compute. You're going to compute a potential for something.
Potential for these scalar fields, but for the expectation, I want to compute this expectation value of phi m.
But
and this potential is gauge invariant. So the potential is gauge invariant. So one can bring the gauge, one can apply the gauge transformations and bring phi I to a particular, the expectation value of phi I to a particular form, whatever that is.
But when you do the calculation, you do it by introducing a source for some field and then Legendre transforming that thing.
Yeah.
What is the field for which you introduce the source?
So this first, so I want to introduce this for phi I.
Phi I. So for a non-gauge invariant quantity.
Yeah. And then this, since the potential itself is gauge invariant. So what that would mean
that's fine. But then in doing that, you would have to work in a particular gauge.
Yeah, you can
do the calculation.
Yes,
Which gauge do you work in?
So you can work in whatever gauge, but one can choose a particular gauge. Like for instance, this I'm going to choose a gauge where this phi I expectation value is diagonal.
So that's your gate choice. This abelianization.
Eventually, I'm going to choose a gauge where this phi I is a diagonal matrix.
Where phi I as a field is diagonal, or only the expectation value?
The expectation value is diagonal.
Well, expectation value doesn't completely determine gauge. If you want to say that
okay,
phi
so
I
you
as
can
a field,
you're saying that I want to consider all configurations which are diagonal.
With this is the Toft gauge, right? The gauge Toft used. Okay, very good. So you're good. This is, and then you'll have u1 to the power n-1 left over.
Yeah. So.
Oh no, because it's bifundamental. Maybe that's it. Sorry. Yes.
Okay, so.
No, but you have something left over, right?
Yeah.
I'll have this entire gauge transformation. I mean, okay. So I'll have something left over, but this would.
Yeah, corresponding U1 from the other side, that would be unfixed.
Yeah, so I think
the diagonal U1s.
Yeah, all the diagonal U1s are unfixed. Yeah, that's what I.
And then you will choose, I don't know, Feynman gauge or something like that for those U1s.
So, okay, just let me. I'll come to the expectation values and probably some of the questions that you're asking. So will be clear. But I'm saying that one can integrate out these fields, these other fields, and just consider the contributions to the scalar fields with the zero Matsubara modes for the scalar fields. Just one can integrate out these all the other fields, the gauge, including the gauge fields and everything, and consider the contributions. So one can basically look at this diagram, and on the two sides you have zero Matsubara fields for the scalar fields, and just integrate out all the other modes, the non-zero Matsubara modes and everything. Does that?
I mean, it sounds to me like you're treating you're computing, like, as you say, the quantum effective action for phi ij, just the field phi ij.
Yeah.
Which, I mean, sounds reasonable. Said that, I mean, it's not a gauge invariant quantity.
Yeah.
And so you perhaps have to be a bit careful.
Yeah. So, but I'm just saying that you will have the ultimately the effective potential should be gauge invariant. So there should be the gauging, the configurations that are related by gauge transformations, they should have the same potential.
You know, if I was going to be an absolutist, I would say that you should be computing an effective quantum effective action for a gauge invariant operator.
Okay, but
here. You know, the quantum effect. Anyway, we'll come back to this later. Please go.
But I mean,
I understand what you're saying.
Yeah, but this is often how it's done, right? In the standard model also, you'll compute it in a similar way, right? You'll give a wave to the eggs with a background, and then you'll compute it. I mean, you're right, you could do it that way, but this in weak coupling is a equally good way, I think, to obtain the effective potential.
To obtain the effective action for what?
you compute the effective action as a function of the scalar fields.
Okay, I think that statement is slightly ambiguous, but let's come back to this at the discussion.
Yeah. So, okay, so one can compute these thermal masses.
Soumyadeep, sorry, if I might, yeah. So let me just fly my, worry here, which is that I'm worried about the large n limit when you take sources for colored objects. So typically, when you do such things, if you did sources like phi1s for gauge invariant objects like phi1 dagger phi1 or phi2 dagger phi2, etc., then eventually you will get an effective action for those guys, and after doing the general transformation and so on, and in which the the n factors will just come out, and they will sit, as a prefactor to the effective action, allowing you to do this, large n classical theory and so on. If you do the same thing for colored objects, for example, suppose you take the eigenvalue stuff, you will still have eigenvalues with lambda 1, lambda 2, lambda 3, etc., hanging around inside your effective action. So as a result, the large n factor n does not come out. So that does not, when you do the path integral over these lambdas, okay, you still have to do some other thing like eigenvalue density or some such stuff to make it a large n kind of saddle point problem. Okay. Otherwise, you can do, of course, all of this stuff, but it's not clear how to do large n if you work in terms of the phi ij's themselves, I mean the phi I matrix elements themselves, or the eigenvalues also, even the eigenvalues.
You're talking about these thermal masses you have in. So here I'm just talking about these thermal masses, right? And I'm just
saying the thermal masses you would define by solving some gap equation, some large n effective action, extremization.
So I'm just saying that if one integrates out the different modes, one would get something of this form, the stress phi I dagger phi I, and that the quotient of that is m thermal I square. So you were talking about these eigenvalues when that is a diagonal entries. So if you work in a gauge where these phi i's are diagonal, and then you're talking about the diagonal entries, right? So something like that. And you were saying that this. So what was your concept? Can you just say once more?
Okay, maybe I can ask later. I mean, what I mean to say is that you are doing perturbation theory here, right? So there are other diagrams. You have to show that the subleading diagrams are down in factors of 1 upon NC1 or 1 upon NC2, etc., etc.
Yeah, that you can show. That is actually these. So one can actually compute all these in finite m, and then ultimately take the n tending to infinity.
Your m thermal I square, they are obtained as a function of
the couplings. They're just functions of the couplings, and one can work with finite n here, and then ultimately take the n tending to infinity limit. So I'm not right now. I'm just you can do all these things in finite n. There's nothing wrong with this. Whatever I'm saying up till now, I'm just constructing this potential. You can do that in finite n. It's only when you try to obtain this so all these results actually are completely. I mean, these things can be done in finite n.
Okay, so let's go back to the So in your self energy diagram, in this diagram, there are propagators which themselves depend on fields or not.
Yeah. So
those fields are what? The eigenvalues?
Okay, yeah.
So then if you're working with such propagators, then I'm not sure how, when you go to the next, like two loop kind of diagram, they would be down by factors of 1 upon 8. You are going to say that this is the only diagram that you need to compute, right?
Oh, this is not a diagram. I'm just saying this is not one particular diagram. This is the class of diagrams that I've represented. This shading just means that there can be many loops. But I'm just considering, eventually I'm going to consider just the one loop diagrams. That's true. But what are you worried about? That the two loop diagrams might be comparable to the one loop diagrams?
Yeah, I'm worried about if you are working with in terms of some, if you're setting up some self-consistent equation in terms of colored objects, then the corresponding.
Is that true in the Veneziano limit as well? Like for instance, where you take the number of fermions?
No, it depends on what your self-consistent fields are. I mean, if your fields are all color singlets, then it's obvious at the, very easily that the subleading terms are down by 1 upon n. But if you are working in terms of colored objects, then it's not immediately obvious. That okay, maybe we can discuss. I don't want to.
Okay. I'll try.
After this discussion of this diagonal gauge, etc., the final diagnostic of the symmetry breaking is just the sign of this thermal mass, right?
Yes.
Which is defined in terms of gauge invariant quantities.
Yes.
So that seems okay, right? That seems fine.
So maybe you can say you're computing the quantum effective action for phi dagger phi.
Yeah, but we know what it is. Just this. I mean, I don't know what you want to say about it, but you can just the diagnostic is this. Now maybe the complaint is that this diagnostic is not of the thing that you want, whether the symmetry is broken or not. But for as the calculation is only whether the EM thermal is less than 0 or not.
Yeah, I agree with you. I think I'd like to hear, but maybe Shiraz would tell us afterwards what exactly your worry is, Shiraz, because I mean, I would do, if you do it for the abelian-Higgs model, right, just to retreat to something very simple, one would do it in the same way, right? You would actually just turn on a wave for phi, integrate out the fluctuations and construct the effective potential, which, as Soumyadeep says, ultimately you would be able to write in terms of gauge invariant. Because then you could see the M square.
Maybe we can talk in the discussion session, because
that would be great. I look forward. Usually you're 3 steps ahead of me, so I'm sure you're worried about some subtlety.
No. I'm worried about a subtlety. I'm probably wrong, but we'll talk about it.
No. I really want to. Yeah.
So if either of these thermal mass squares are negative, then the minimum of the effective potential lies away from the origin in the field space, which would imply a non-zero value of these expectation values of these fields, and which in turn would imply that the respective baryon symmetry is broken. And I will show that under certain conditions, the same thermal I square can be negative for some of the fixed points of the double bifundamental. So this is the statement. So okay, so in fact, these real double bifundamental model and complex double bifundamental model that I talked about are dual to each other in the large N limit. There's an orbifold equivalence, where the parent theory is this real double bifundamental model with rank 2 NCI and 2 NFI, and the number of flavors of fermions with 2 NFI. And the complex double bifundamental model, the rank is NCI and the number of flavors is NFI. And the relations between the couplings is as follows, as given here. So the superscript C or R just indicates whether it's the real double bifundamental model or the complex double bifundamental model. So, and the thermal masses in the two dual theories are equal. So this duality ensures that whatever I'm going to say about this real double bifundamental model, also there would be a similar result for the complex double bifundamental model. So I'm going to stick to this real double bifundamental model, the analysis of the real double bifundamental model.
See. Hey, say once more, I was sleeping. Yeah. What Veneziano limit again? Sorry, just once more.
So this is the limit.
Okay.
So the ranks are taken to infinity, and the NFI and NCI ratio is XFI, and the ratio of the two ranks is R, and the coupling scale in this way.
Okay. Which is just the natural scaling with N.
Yeah, but when NFI is large, the number of fermions.
I understand. You have to scale the flavors.
Okay, so
thank you.
So right, so let's now talk about the fixed points. I'm going to talk about the fixed point of the real double bifundamental model, and to determine the Banks like fixed points in this model, I would have to go up to 2 loop beta functions of the gauge couplings, which are of this form, and the 1 loop beta functions of the quartic couplings, which are of this form. So one thing to note here is that these beta functions do not depend on this ratio R, which is NC2 by NC1. These are the planar beta functions. The planar beta functions are independent of this ratio, NC2 by NC1, which is important. So all models from the point of view of these beta functions, all models, this R value, the value of R is immaterial. So the beta functions are the same.
Hey, Soumyadeep, sorry
Yeah.
to slow you down. I'm still processing what you said on the previous slide. I did not understand this duality statement. Don't the two theories have different global symmetries? Like one had...
There's just this U1 and Z2 symmetry, but that would lead to an additional Goldstone boson. But but you have a large number of particles, say, and you have just one single Goldstone boson that you have.
Okay, no, I meant something more, which is, maybe I misunderstood. Didn't you have complex fermions in one case? So you had the global symmetry with U, N, F1 cross U,
Yeah.
and F1 like that. In the other case, it was SO. Isn't that right?
Yeah, in the other case, it was O.
Oh, so then how are the two dual to each other if they have different global symmetries? I missed that.
So basically, you have this two NCI, two NFI.
Sure.
The ranks and the
SO like that.
Sorry.
No, but it's an orbifold equivalence, Sandeep. It's not equivalence.
Orbifold. It's an orbifold.
It's an orbifold. Yes.
Ah, okay. I see. So you probably break the SO2NC to the U. Okay, so I'll have to process this.
Yeah.
Okay.
So this is the parent theory.
Okay. Thank you.
That's fine.
Go ahead.
Yeah.
Yes. I didn't appreciate the.
And this is a large N statement, right?
This is a large N statement, N tending to infinity. Yeah.
Yes, I mean, at a practical level, it's just a statement that any large N diagram involving SO and any large N diagram involving U are basically the same up to some factors of 2 in the counting of N.
Yeah. So
is that right? I see.
Yeah.
I see.
So, okay. So
and also one thing confused me. This Goldstone boson that you talked about for the U, SU case. You said there is only one, or there should be two, because we have two U1s. Which will be spontaneously broken. So there should be two of them, right? Or they're somehow tied together by...
Yeah, there would be two of them. Yeah, there would be two.
So there are two?
There would
no,
be
I mean two in each sector.
Two in each sector, yes. I think so, yeah. Because both the U1s would be broken.
I see. No, but I was wondering, because the wave, this is coming from the wave of the bifundamental, there should be one, even though the breaking is of the... Even the breaking is of two, there should only be one Goldstone, because the thing that is breaking it is bifundamental.
Right. Yeah. You're right. Yes. That's true.
Okay.
That's true. So you'll have just one gauge one parameter family of thermal vacuum, and and the Goldstone boson would be the generator. Yes. Yeah. Okay. Right. So the beta functions have this property that they're independent of this ratio, and by setting the beta function of lambda I equal to 0, one gets this solution. Lambda I is this quantity, and we can choose xfi to be 21/4 minus epsilon I, where epsilon I is a very small number, small but positive number, and that gives you a weakly coupled. That basically keeps lambda I small at the fixed point. And similarly, setting beta hi to 0, one gets these two solutions. So again, one thing to note here is that Fi and zeta, the double trace couplings, did not appear in the expressions of the planar beta functions of lambda I and hi. So we could find the roots independently. And one can show that this persists at all orders in the planar limit. Although I just looked at the one loop and the two loop beta functions, it persists at all orders actually. So plugging these solutions of lambda I and hi into beta Fi and beta zeta, the one loop beta functions of this, one can find the roots of these beta functions. So there is a discrete set of roots when the two sectors are decoupled, but that's not interesting because the baryon symmetries in both the sectors for those fixed points remain unbroken at non-zero temperatures. So that we have checked, but that's why we actually had to consider this coupled model, where you have this more complicated model. Otherwise, we could have just studied just one copy of this and not included two sectors and so on. So the roots with zeta not equal to 0 are generally complex, leading to non-unitary fixed points. But one can show that to get a unitary fixed point with zeta, one can get a unitary fixed point when zeta is with zeta non-zero, when xf1 is equal to xf2 equal to xf say. In that case, lambda 1 would be equal to lambda 2 equal to lambda at the fixed point, and when h1 and h2 are equal. So there were two roots for each hi. So if one choose h1 and h2 to be equal and to choose a particular root, which is this minus sign, then one can actually find real solutions to the couplings, and those will give the unitary fixed points. So to study these unitary fixed points, it's convenient to switch to these coordinates fp and fm.
Sorry, I've forgotten what zeta is, please show me.
Zeta is the coupling that couples the two sectors, the phi's in the two sectors. Zeta is this, which couples the two. Zeta is this.
Thank you.
And phi's are the double trace couplings in the individual sectors. Okay. So in terms of this, one can actually take linear combinations of f1 and f2 to construct fp and fm. So fp is f1 plus f2 by 2, and fm is f1 minus f2 by 2. And in terms of these couplings, the beta functions have this form. So these are just the double trace couplings, the beta functions of the double trace couplings, and they have this form. And now if we search for fixed points with zeta not equal to 0, then the last two equations, one can see that the last two equations are degenerate and can be satisfied by setting this coefficient to 0, 16fp plus 32h minus 6 lambda equal to 0, which implies that, and one by substituting the values of h in terms of lambda, one can solve for fp, and finally setting beta fp to 0. So this
Hi, why is that why does those two couplings get related like this?
So this is a consequence of, this is a feature of this the beta functions in these models, that there is a degeneracy. That is, you have a fixed circle. I was saying that instead of discrete set of points, you have a conformal.
Oh, the circle is in these two variables.
Yeah. So the circle comes from finally setting this beta fp equal to 0, which sets a value for this fm square plus zeta square. So you have h in terms of lambda from the previous equation, which is 3 minus square root of 6 by 16 lambda, and fp is square root of 6 by 8 times lambda. So finally you can solve for zeta square plus fm square, and that's a number. So we have explicitly checked that this fixed circle actually survives in the planar limit under two loop corrections, and in fact we have given a argument up for that it survives at all orders in this limit, in the planar limit. Okay.
So Soumyadeep, actually, so usually we don't find such fixed, such modulus for non-supersymmetric conformal theories, right? But so is this the first example of
where we have
circle?
I think so. At least as far as I know, this is the first paper to actually. This was in the paper that we wrote back in November, and we gave an explicit proof at all orders. It's a diagrammatic proof. It's pretty long, so I'm not going to talk about it in this talk in this seminar.
Hey, could you remind me if the exercise was same? Sorry to interrupt.
Sorry, which one?
Were the exercise same? The xi, the ratio of the color to flavor?
xf1 and xf2 are taken to be the same. Only then you have unitary fixed points where the two sectors are common.
So in that case, probably you could. This is some rotation between the between the double trace potentials, right? Like probably in the larger limit, you could. I mean, is that a right way to think about it? Like
maybe
mixing,
but
the
I don't know. I
double trace
I don't know of a simple argument, like some symmetry transformation in the larger limit, but I don't know.
Yeah, I mean, I was wondering in that double trace part of the thing, you're kind of mixing the single sector.
Mixing, but I'm saying that I don't know of a simple transformation, some argument based on some simple transformation which holds at large limit. It's the proof that
I was naively wondering, like, since in this Venetian limit you're explaining, like, say if you're putting x's to same, then there's not much room, right? You have some large n and then the flavor to color and all is fixed.
But how do you go from that to the fixed circle? I mean, that's, yeah.
Okay. Okay. Thanks.
Okay. So anyway, so so let's look at the thermal effective potential, and one can actually show that the quartic terms are positive definite. That I'm not going to harp on right now, but one can show it, and one can also look at the thermal masses, and these are the interesting objects. So one can show that all if you take NC1 to be greater than NC2, it is if you take the second sector to have the smaller rank, then M thermal 1 square is greater than 0 for all points on the fixed circle, whereas M thermal 2 square can be negative only when R is less than a particular value. Okay, and so one finds that there's an angular interval on this fixed circle.
What was R again, please? Sorry, I'm getting lost with your symbols. Sorry.
Small r is the ratio of the two ranks, NC2 by NC1.
Thank you.
And okay, so one can actually.
Sorry, Soumyadeep, sorry. FM was what? I got a bit lost.
FM is okay. So FM is F1 minus F2 by 2.
Acha, okay, got it.
Yeah.
Fine.
And similarly, FP is F1 plus F2 by 2.
Fine.
Okay, so one can actually go to a polar coordinates, since you have a circle in the FM zeta plane. Okay. One can go to a polar coordinates, which is FM is equal to R sine theta and zeta is equal to capital R cos theta. And in this in these coordinates, this for each value of R below this upper bound, for each value of small r below this upper bound, one has an angular interval which is given by this. So this is a graphical plot. So you have an angular interval whose lower bound is theta 1 and the upper bound is theta 2. And for each value of small r, you have an angular interval, and there's a value of r beyond which there's no such fixed point where M thermal 2 square can be less than 0. So there's a maximal value of small r beyond which one doesn't have symmetry breaking in the second sector, basically. Okay, so the symmetry is always, so there's a completely analogous story for r greater than 1, where the symmetry in the sector in the first sector would be broken. The baryon symmetry in the first sector would be broken. But in this case, I'm focusing on the case where NC2 is less than NC1. You can choose to call the second sector to the smaller sector to be the second sector, and then this is the result, that there is a maximal value of R, which is roughly around 0.19, and below this value of R, you have an angular interval where M thermal 2 square is less than 0. And this, I would argue, means that the baryon symmetry in the second sector is spontaneously broken at non-zero temperatures. So this is the statement that for the fixed points at which M thermal 2 square is less than 0, we can find the thermal vacuum. So you have this potential, you have the form of the potential. You can solve the potential with this choice, with this gauge choice, where the diagonal entries of the matrix are non-zero, rather you choose the matrices to be diagonal, and then you can solve for them, and this is the solution that you get. These are the solutions, that phi 1 is equal to 0 and phi 2 has this structure, and this means that the baryon symmetry in the second sector is broken, and there are two gauge inequivalent vacua which are distinguished by this plus and minus sign, and they are related by the broken baryon symmetry that I talked about. Okay.
But just show that again. Sorry. So two distinct, yes, and two gauge invariant inequivalent vacua. Because of the plus and minus.
Yeah.
So baryon number, I see. The baryon number is different. Okay, thank you.
Yeah.
Okay. Right.
Sorry, Soumyadeep. So you're computing the value of this phi dagger phi, and you're looking at its sign, the thermal mass. Now the effect you get is a one loop effect. So it's small compared to the classical action, right? Terms in the classical action.
So what is the classical action? What do you mean by the thing?
You
The
had,
classical action is also one also has linear terms, right? You have things that are linear in the couplings. So this is the quartic piece that you had, right?
yes.
So these are also linear, and the thermal mass that you compute is also linear, right?
So and the coupling is what is the coupling here? What is the thing that is justifying one loop versus two loops again, please? This
one loop versus two loop. I'm just computing the thermal masses up to one loop.
Yeah, and what is the parameter that suppresses two loops compared to one loop?
The toothed couplings. The toothed couplings that I have.
The toothed coupling, and that is determined by the being at the fixed point of the RG equation. So what does it work out to eventually?
Sorry.
The toothed coupling is determined by the ends in your problem, right?
The toothed couplings, that's what I showed, right? The toothed couplings are the
you've showed a lot, but I don't remember everything.
Oh, sorry. So okay, so the toothed couplings are basically this lambda 1. These are the values at the fixed point. Lambda 1 equal to lambda 2 equal to lambda. H1 equal to H2 equal is 3 minus square root of 6 by 16 lambda.
Everything is fixed in terms of lambda, the gauge 2
yes.
coupling.
Yeah.
So that is the thing that controls.
I'm choosing to be small.
And what was lambda, please?
Lambda is the common value of the tooth couplings corresponding to the gauge coupling. So lambda, okay. So let me just. So this is lambda. Gi square is 16 pi square lambda I by NCI.
Wait, but isn't lambda also fixed by being at the?
Yeah, lambda is fixed. Lambda is fixed in terms of this. At the fixed point, lambda has this value. This is the value, and I'm choosing xfi to be 21 by 4 minus epsilon I.
Okay, so in the end, this epsilon I is what controls.
Yeah, epsilon I is the controls perturbation.
So lambda I is small because of that. Okay, yes. Excellent. So now in this lambda I, what I just wanted to get a sense, what is the order in lambda I of the final answer for the coefficient of the quartic term in the potential versus coefficient of quadratic term?
Both of them are order epsilon.
Both are order epsilon. I see.
Yeah.
So you say you get a wave of order 1 when you extremize. The wave is not itself small in epsilon when you minimize your effective action.
Yeah, you can see this actually. So for instance, this M thermal 2 square, these thermal masses are order epsilon.
Okay.
Whereas this H plus F2, that's also order epsilon.
H plus F2, these are coefficients of the quartic terms?
Yeah, and they are order epsilon. Everything is order epsilon.
So then if you extremize the full effective action to find where phi would be, it would be order 1 in epsilon counting.
Yes.
Okay, thank you.
Right. So for each of these backward, the residual gates.
One question. So here you had lambda 1 is equal to lambda 2?
Yes, I chose xf1 equal to xf2. That's my choice. That I can choose. And once you choose that,
at some point you were also talking about two gauge couplings being the same, right? You always want to keep the gauge couplings the same.
Yeah.
But isn't that in contradiction with this? Because now you are saying lambda should be the same.
The two gauge couplings are the same. That's why you have the same values for the two GIs. That's for small GIs, which means that you just have one GI for each sector.
Right.
But corresponding lambda I. And now
but how can you take the lambda is also to be the same? Because there is a factor of NCI there, right? NC1 and NC2, they are different. So if you take the G's to be the same, then you cannot take the lambdas to be the same. Maybe I'm misunderstanding.
No, the GIs in the two sectors are not the same. The GIs.
Oh, right. Sorry, it's the other thing, right?
There are two twos.
Yeah.
There are two twos.
Yes, thank you. Yeah. Sorry.
Okay, so you have this conformal manifold, okay. So right. So for each of these vacua, the residual gauge symmetry in the second sector is SONC2. So you had an SONC2 cross SONC2, and one can see this by considering a transformation of this form where O1 cross O2, which belongs to SONC2 cross SONC2, and by transforming this wave. So you demand that what are the gauge transformations that keep this wave invariant, and one finds that O2 is related to O1 in this way.
Wait.
So,
This. I'm sorry. Just go back and show that wave again.
yeah.
Now this is what I'm a bit confused about your SOs and SUs. But just given this, wouldn't you? I thought you would say it's UNC1 minus 1 or UNC2 minus 1 cross U1, because you have equal eigenvalues for NC2 minus 1. No?
Equal eigenvalues for NC2 minus 1.
One of the eigenvalues.
Yeah, but yeah, but these are gauge transformations, right? So
yeah.
So I'm saying that for what are the right.
I mean, what
so
I'm
the
saying
question,
is there a left and right UNC.
So I'm choosing a particular wave, and then I'm asking what are the transformations, what are the gauge transformations that keep that wave invariant.
Yes, I agree. And under, let me just do the U model. The SO I understand little less well.
So in that case, this would be e to the power I theta.
That one.
This first term would be e to the power I theta.
I theta. Okay. The rest. What about the rest? What would that have been?
1.
1. Okay. And that theta can take any value or what?
From 0 to 2 pi.
Any value, huh?
Yeah.
Then would you, just so I understand, would you have said that the symmetry which is left is UNC2 minus 1 cross U1? What do you think? You know what all I'm saying is under the two gauge groups with rank NC2, the phi transforms under a left and right action, right? Isn't that true?
Yeah.
So because all your waves ends, I mean, except for one, all your waves are the same, no?
Yeah, okay.
So doesn't that preserve out of the product group a UNC2 minus 1 gauge symmetry?
Actually, why is this not e to the I theta everywhere? You know, just that diagonal e to the I theta everywhere.
You can take that as well. That's equivalent.
But if you take that, then it's clear that the full diagonal is preserved because it's just the identity matrix.
Then you can do that. You can actually you can show that this is equivalent to the baryon symmetry that I talked about. That is equivalent to taking e to the power I by considering a similar transformation by e to the power I theta by n. That you can do. Transforming all the scalar fields by e to the power I theta by n in the complex double by fundamental model. That's true.
So now
in the real double by fundamental.
Sorry, if all the waves are equal, then wouldn't you have just UNC2 as the unbroken symmetry?
Sorry, if all the waves are equal, all the diagonal entries are equal.
Yes. That's
but e to the power I theta by n. Okay, so let's be clear about what is the, okay, so that's the configuration that you want to consider. And then what are you asking? Sorry.
Well, I mean, in response, maybe I misunderstood. I thought in response to Abhijit's question, you said, I'm not sure I understood it, that the waves, by waves, I mean only the diagonals, forget the rest because you're not giving them any expectation value.
Yeah.
So I thought you said all the waves could be taken to have an equal eigenvalue, e to the I theta. Is that correct? Or maybe that itself was not right in my side.
You can consider these kind of, you can go from one by a gauge transformation, you can bring it to that form. That's true.
But that confuses me. I mean, if the eigenvalues are unequal, you have a smaller gauge symmetry left unbroken, I would have thought. If they are all equal, you have a bigger gauge symmetry. No? That's what I would have thought. For example, if all are equal, take that case, wouldn't you have a UNC2 gauge symmetry left unbroken? Because it's just some number times the identity matrix, which is left invariant under U, that identity times U dagger.
Okay.
Or any U. No?
Yeah.
So what I'm a little...
Okay, so you have a UNC2 minus 1. You're saying UNC2 minus 1. But that's a subgroup. Wouldn't that be a subgroup of this SUNC if you consider SUNC2? It's a subgroup of SUNC2, right?
Sure.
Sorry, because it's bifundamental, perhaps it's a bit unfamiliar, Sandeep. But just to see that this is equivalent to what Abhijit said. Suppose I had e to the power I theta on the first and 1 on the second. Then I could just act with an SUN just from the left. By e to the power I theta by n in the bottom elements, and e to the power minus I theta, just make them all these eigenvalues equal. You could do that, right? So it's clear that that's equivalent to what Abhijit said.
Yeah. So I was.
So because it's bifundamental, I think you can do more than what you're saying, though I can't see the details.
Yeah.
But if you put it in this language, then it's clear that it's UN that's preserved, right? At least a UN is preserved.
Okay, I see what you're saying. Okay, very good point. And perhaps I'm a little an unfamiliar terrain, but if you can make all the eigenvalues equal, then don't you at least expect a full UNC2 group?
UNC2 minus 1, right?
Well,
you're talking about UNC2 minus 1.
That's what I was saying first, but then now, this argument of Abhijit and Shiraz and all, won't that suggest UNC2 itself? Am I missing something now? All equal eigenvalues, why not whole UNC2?
Because
what was your final answer, Shoumyadeep? You had it on the next page? What was your final answer for the unpreserved?
So in this case, this is the SON. So this is what I was saying, that O2 is related to O1 in this way. If you just take the vacuum,
just in the SUN case, what was the unbroken part of the gauge?
SUN, you have SUN cross SUN in that sector.
And it was broken down to SUN?
Yeah, this is by a similar argument.
Yeah, so then agrees with what you're saying, right, Sandeep?
Oh, okay. Sorry, now I understand. I thought you, okay. Fine then, fine. Thank you.
Yeah.
Thank you. Thank you, Shoumyadeep. Go ahead.
So this is this means that half of the gauge bosons in the second sector are Higgsed, because the half of the generators in that sector are broken. Okay. So, right. So can you tell me how much time I have? Because I've just finished the discussion of the CFTs, and I wanted to talk about this marginally relevant deformation. So how long do I have?
We had quite a few questions during the talk, but how long do you think you would need?
Maybe 10 minutes. Is that fine?
Okay, so let's try to finish in 10 minutes then.
Yeah.
So we can postpone the questions till the end, if we can.
So let us now look at certain marginally relevant deformations of the points on the fixed circles. So the deformations that I will consider will involve only the double trace quartic couplings that I had, F1, F2, and zeta. And the beta functions of the single trace couplings, as I had mentioned, this lambda I, the gauge coupling and the single trace quartic coupling HI, they do not depend on the double trace coupling in the planar limit. So one can keep these lambda I and HI frozen at their fixed point values, which are these, as I had mentioned earlier. And then one can introduce deformations in the double trace quartic couplings, and one can show that okay, so the RG flows in this case, the RG flows triggered by these deformations are going to stay restricted in the subspace defined by these values of lambda I and HI, because lambda I, HI are not changing along the RG flow. So to study these flows, it is convenient again to go back to these polar coordinates in the FM zeta plane. Fm is equal to, where Fm is equal to r sine theta. Fm is, again, let me just remind you, Fm is F1 minus F2 by 2. So Fm is equal to r sine theta and zeta is equal to r cos theta. And so the planar beta functions of Fp, capital R, and theta in the subspace lambda 1 equal to lambda 2 equal to lambda and h1 equal to h2 equal to h take this form, where you have beta Fp is a function of Fp and R, beta R is again a function just of Fp and R, and beta theta is equal to 0 when R is not equal to 0. In fact, this is what led to the appearance of the conformal manifold in the first place. That is, since this beta theta vanishes, So if you have a solution for F1 equal to F2, that's capital F1 equal to capital F2 equal to 0, then you can just, and that solution is just solution of Fp and in terms of Fp and R. So then you can, this theta variable that just traces that just generates a conformal manifold fixer. So one can show, based on the one loop beta functions that I had earlier, one can show that these functions F1 and F2, capital F1 and capital F2, these have these forms. As I mentioned, the vanishing of beta theta means that the projections of these flows on the FM zeta plane is radially directed. And furthermore, since the beta functions of Fp and R are independent of theta, these flows are identical for different values of theta. Okay. So these features lead to the fixed circle, as I mentioned, and at the points on the fixed circle, we have F1 and F2, these vanish, and let's say the value of Fp and R at these fixed points are F0p and R0, and I had already derived these values earlier, the radial distance of the fixed circle and the value and Fp and the value of Fp, these are given by these expressions in terms of lambda. At leading order in lambda, these are the values of Fp and R at the on the fixed circle. So now one can consider small deformations of Fp and R from these fixed point values, which are given by Fp is equal to F0p plus delta Fp and R equal to R0 plus delta R. So the flow of these deformations, delta Fp and delta Fr, at linear order in these deformations are given by these partial derivatives. And the coefficient matrix multiplying the deformations in these equations are of this form. This coefficient matrix has this form. And by substituting the expressions of F1 and F2 that I had written here, the F1 and F2, the functional forms of F1 and F2 are given here. So by substituting these values, one can show that this matrix takes a very simple form. This is just 16R0 times sigma 1. Sigma 1 is the Pauli matrix. So hence the one of the Pauli matrices. So the eigenvalues of these matrix and the corresponding eigenvectors are as follows. So the eigenvalues of the sigma of the Pauli matrices is 1 and minus 1. So you have a 16R0 factor multiplying it. So you have minus 16R0 and 16R0, and these are the eigenvectors. So if you choose the eigenvalue with the negative sign, that gives you a marginally relevant deformation. And if you choose an eigenvalue with a positive sign, then that gives you a marginally irrelevant deformation. So I'm going to focus my attention on the marginally relevant deformation, where the corresponding eigenvector is 1 and minus 1. So, and I'm going to take the marginally relevant deformation to be of this form. Delta Fp is equal to minus delta R is equal to R0 by 2. And epsilon tilde is a small parameter which determines the strength of the deformation. I'm going to take epsilon tilde to be 1. And these values of the deformations are taken at a particular reference energy scale lambda, capital lambda. So the RG flow generated by the one loop beta functions lead to the following values of the couplings at a scale mu, where this is the flow. The flow is determined by this T. T is ln mu by lambda, and K is 1 minus epsilon tilde. So these are the functional forms of Fp and R as a function of T. As T tends to infinity, you have this there are these tan hyperbolic functions that appear in these expressions. The tan hyperbolic function 8R0t, tan hyperbolic of 8R0t, that goes to 1 as T tends to infinity. And it goes to minus 1 as T tends to minus infinity. So one can show that in the first case, that is as when T tends to infinity, that is when you go to the UV regime. T tends to infinity means that you are taking mu to infinity, which is the UV limit, and in the UV limit you go to this fixed point. On the fixed circle, Fp is equal to F0p and R is equal to R0. This is this is a point on the fixed circle.
Sorry, very quick question just to understand what was R0?
R0 is the value of, so R is the radial distance along this in this FM zeta plane, and R0 is the value of R at the fixed circle.
And
this
was order epsilon, right?
This was order epsilon.
Thank you.
So I'm considering deformation, small deformation in the radially inward direction from this point on the fixed circle. And then what I'm saying is that in the UV limit, you just go back to the fixed circle. In the IR limit, it just goes to the point R equal to 0, and that which corresponds to the two theories being decoupled, because R is basically the radial distance in the FM zeta plane. So when you take R to 0, it means that both FM and zeta, they go to 0. The zeta going to 0 means that the two sectors become decoupled, and FM going to 0 means that F1 is equal to F2. So it's just, you have a symmetric fixed point where F1 equal to F2 equal to something, and zeta is equal to 0. So this is the IR limit of this theory. So you have a non-trivial fixed point in the UV limit living on this on this fixed circle, and you flow down in the energy scale, and you go to a theory with where the two sectors are decoupled. So as I had mentioned, some of the fixed points in the UV regime. So this is the graph, but yeah, this is the graphical plot of these this RG flow that I mentioned. So the point is that in the UV, so this fixed circle, as I had mentioned earlier, that for a subset of points on this in certain parameter regimes, a subset of points on this fixed circle exhibits thermal order, whereas the IR fixed point, where the two sectors are decoupled, that lacks this thermal order. There the baryon symmetries in both the sectors are unbroken at any non-zero temperature. So this theory that I have now, effectively is described by this UV fixed point in the high temperature limit. The thermal behavior of the UV fixed point determines the high temperature limit of this field theory, and the thermal behavior of the IR fixed point that determines the low temperature limit of this same theory. And the thermal behavior of the UV fixed point exhibits thermal order, exhibits an order phase, whereas the thermal behavior of the IR fixed point is in a disordered phase. I mean it's in a disordered phase. So basically, this means that when you the theory, the systems defined by these RG flows, when you in the low temperature limit, they are disordered, and they are in a disordered phase. And as you increase the temperature, they go to an ordered phase where the baryon symmetry in one of the sectors is spontaneously broken. Okay, so this is the essential point. And one can track this completely because you have a weakly coupled theory throughout this RG flow. One can track this transition, and one can actually come up with a quantitative estimate for the critical temperature by again looking at these thermal masses for the two scalar fields. And one can, to avoid the appearance of large logarithms in the thermal perturbation theory, one can take this the renormalization mu to be equal to T, so that this ln mu by T, these kind of terms that appear in the thermal perturbative expansions, they are small. And then one can do is that one can track the evolution of this thermal masses with as you increase the temperature. So one can here I have shown the graphical plots of these thermal masses for a certain choice of r, theta, lambda, and epsilon tilde. That's fine. But essentially, this is what one finds, that the thermal mass of the scalar fields in the first sector that remains positive throughout the at all temperatures, which means that the baryon symmetry in the first sector remains unbroken. On the other hand, the thermal mass of the scalar fields in the second sector They are positive in the low temperature limit, but as you increase the temperature, they become negative, and they in the high temperature limit they remain negative, which means that the baryon symmetry in the second sector remains broken in the high temperature. And the critical temperature is given by the point at which this thermal mass in the this m thermal 2 square that goes to 0. So one can just solve it, and it has this form. The solution has this form, that Tc is just ln of Tc by lambda. Lambda is the reference energy scale where I had introduced the deformation. And one can actually see that this Tc has a real solution only when the UV fixed points lie in the regime that I mentioned earlier, which shows where the CFT corresponding CFT has thermal order, that is theta has to lie within theta 1 and theta 2, and R has to be smaller than a particular value. So R has to be smaller than a particular value, which I had mentioned earlier. There's an upper bound on R for which small r, which is the ratio of the two ranks. There's an upper bound that I had mentioned somewhere. Yeah, so this is the upper bound on R, above which there's no symmetry breaking for the UV CFTs at finite temperature. So as long as you stay with it, as long as the UV fixed point has thermal order, you have such a symmetry breaking at high temperature in the QFTs defined by the marginally relevant deformation. And this is a phase diagram for this system, where the red line separates the two phases. The first phase, the high temperature phase, in this case is given by the baryon symmetry, is a phase where the baryon symmetry in the second sector is broken. And there's another phase, phase 2, where the baryon symmetry in both the sector are unbroken. And the red line separating the two phases gives the critical temperature for the different values of theta. Okay, so this is more or less what I had to say, and let me just summarize. So in this talk, I discussed examples of 3+1 dimensional large gauge theories where certain global symmetries are spontaneously broken in the high temperature limit. I showed that these models have certain fixed circles in the planar limit, and under appropriate conditions, an angular interval on this fixed circle exhibits symmetry breaking at non-zero temperatures. The broken symmetry is a baryonic Z2 in the real double bifundamental model, and U1 in the complex double bifundamental model. This spontaneous symmetry breaking, I argued that it is accompanied by the Higgsing of a subset of gauge bosons. I also showed that there are marginally relevant deformations of these CFTs, which lead to an IR fixed point that lacks thermal order. And these systems undergo a transition from a disordered phase to an ordered phase as the temperature is increased. And I also showed a way to estimate the critical temperature corresponding to this phase transition. So let me just enumerate some future directions. So one can ask how the story changes when one introduces finite end corrections. So we have done some perturbative computations for the real double bifundamental model up to 2 loops. And what we finally concluded that this 2 loop, as long as these 2 loop, if you just look at the 2 loop contributions, they do not lift the degeneracy. So it may be true that if one includes higher loop corrections and finite end corrections as well, while staying in this regime where 1/n is much less than the two couplings, it may be true that at higher order this degeneracy is lifted.
Sorry, while staying in what regime, Soumyadeep?
The 1/n is much less than the two couplings, which is the standard.
But if
regime.
n is finite, then there's no. I mean, if n is 10.
Oh no, I'm talking about finite end corrections where while staying in this regime, if you take n to be too small, then this.
No, but okay, say n was 1,000,000. Would you expect this circle to survive as an absolute statement at n equals 1,000,000?
I don't know. I mean, it depends.
Sounds very unlikely to me, right?
Yeah, I don't know. I'm saying that you're asking whether there's a conformal window above which the conformal manifold suddenly appears.
Yeah, I mean, presumably there are some solutions on the circle, but that it survives as a circle sounds very unlikely.
Maybe, I don't know. I'm saying that the two-loop beta functions are not able to resolve that.
Even that sounds incredible, unless there's some symmetry explanation.
No, if you just look at the two-loop beta functions up and take n to be as small as you like, then yeah, then the degeneracy is lifted. That's for sure. What is surprising is that if you systematically do this 1 over n correction, that is, you take 1 over n to be small, but work in this hierarchy where 1 over n is much less than the two couplings. So then what happens is that perturbative computations, two-loop perturbative computations are not able to lift the degeneracy, because then you need, so there's some interplay of this perturbative expansion, and then you need.
No, but in the end, the question is, are there any finite values of n at which you have the circle?
Yes.
No matter how large, are there any finite values? That sounds very unlikely, right?
Yes, that's true, because that would require some other argument. I mean, like something apart from just perturbative computations, some symmetry argument, something like that, which I am not able to see.
Okay.
But I'm also not able to find the. I'm also not able to find the point which survives. That's the problem.
Yeah.
Even if the degeneracy is lifted.
Yeah. So the key question is whether the point that there is at least one point that survives in the place where the UV restores the symmetry, right?
The symmetry.
The place where the UV restores the symmetry, right? And that's not clear yet, you're saying.
Yeah.
Okay. Thank you.
Siraj, you're saying you expect even the non-planar corrections to lift the circle, or just finite n effects? You muted, Siraj.
I would expect it to be lifted at some order in non-planarity.
Okay. So it's not clear right now to me. I mean, at what order is it lifted? I mean, is it lifted at the first 1 over when one considers first 1 over n corrections? I don't know, because I tried to do this computation with two-loop beta functions, and either one has to do that, and that doesn't lift the degeneracy, or one needs some resummation technique, something like that, which I don't have right now. I mean, I don't have the argument of, I mean, whether the degeneracy is lifted at some particular order in 1 over n, or even if it is lifted, what are the fixed points that survive?
Just to say, there's a toy model of this, which is that if you just take ordinary ON sigma model and you in 3 dimensions and you take the 5 to the 6 coupling.
Yes.
The beta function for that at leading order and large n is 0.
Vanishes. Yes.
Vanishes. But at first non-trivial order and large n, its non-vanishing has been computed.
Yes.
So that was the toy model I had in mind for what you were saying.
Yes.
But I find it surprising if it was anything else. But of course,
there the simplification is that in the large n limit you can exactly solve the beta function.
Yeah, exactly. So there you can compute it exactly. Yeah.
So that's the problem in case of these gauge theories. Even the large n limit.
I understand. You can only do computation theory. Yeah.
Yeah. So you have you can study some general features, but it's very hard to get a solution. But yeah.
Yeah.
Okay, so the question is, are there other finite n CFTs which demonstrate such spontaneous symmetry breaking at non-zero temperatures? And there is a recent work by Noam Khai, Anatoly Demarsky, and Michael Smolkin, which basically extends the work that we did with the Wilson-Fisher fixed points to some 2+1 dimensional non-local theories. Similar models, but 2+1 dimensional, but they are non-local. And they found such symmetry breaking at non-zero temperatures for some Z2 symmetries, +1 dimension. Okay, so and can one identify some universal features of this class of CFTs? Like, can one use something like conformal bootstrap at finite temperature, something to identify some universal features, like to see which symmetries, even in the larger limit, even if it is true for larger. I don't know, but I'm interested in finding such features should classify such CFTs. allow one to classify such safeties. And finally, it would be also interesting to find holographic conformal field theories which show this kind of a behavior. And in this case, in the dual theory of gravity, this would mean a violation of the no-hair theorem for the black holes. So these thermal waves in the CFTs that you would get would correspond to hairs for the black holes. In this case, for instance, some baryonic hairs for the black holes. But yeah. So with that, I would conclude my talk. Thank you for your attention. Yeah.
Thank you very much, Soumyadeep, for a wonderful talk. We have had many questions already, but if you have more questions, then please go ahead.
Yeah, Shobhandeep, I mean, a very nice talk. I mean, I can't figure out about the zeta coupling, the left-right coupling.
Yeah.
Whether secretly it is actually, it involves only trace phi 1 square and trace phi 2 square, but I can't see that happening.
Why
the coupling between the left and right zeta stuff. Sorry, not zeta. Zeta is of course like that. These HI fellows.
Yeah.
These guys, maybe I am not. The phi J. What is this? Sorry, these are all in the first. So this is in the left sector alone.
Yeah.
Yeah, you have separate couplings in both. Right?
So HI and FI are just, HI is a single trace quartic coupling
so is it like in effect, okay, is it like in effect some, I can think of these as a square matrix and is a trace of a square matrix to the power 4? Is that what the thing is?
Yes.
Yeah, so why can't you just think of, okay, so maybe I don't understand how to handle the HI tilde fellows, but the other guys, you could just...
No, but there's a systematic Largen expansion in this case. The HIs are just go as 1 over NCI.
Okay, maybe the HIs are
1 over NCI and FI tilde goes as 1 over NCI.
Okay, I take that this double fundamental guys somehow behave perhaps like square matrices and so on. But I'm saying that then why couldn't you take your order parameter, I mean the your variables, gauge invariant variables to be just the phi I, phi I dagger phi whatever. I mean the phi dagger phi from both sectors, left and right.
Yeah, you can take that. Yes, that's true.
You mean trace of phi dagger phi, Gautam?
Yeah. Yes, sir, sorry, sir. Yes. Trace of phi.
No, trace of phi dagger phi is not. This is not trace of phi dagger.
Oh, so H. Sorry. So the H guys are a bit of a problem.
Yeah.
If the H guys were not there, so now okay, all right. So now with the H guys, how do you
But phi dagger phi has a nice transformation. I mean, like it's just it transforms in a certain way.
No, that all is fine. I'm so this, yeah, no, okay, no, sorry, I take this back. Then it is like a trace phi square whole square and a trace phi to the power 4. So how do you do this stuff?
Could I make one comment about this, please, if that's if that's okay? I think I was worried about the same thing you were worried about, Gautam. But I think the fact that he had both his thermal masses and quartic terms of order epsilon, so that his final phi was order 1, I think that makes it clear that his conclusion is correct. The problem is that composite operators are not just functions of the operators, right?
Yes.
That if you make sense somehow of an expectation value of phi, expectation value of determinant of phi will not necessarily be that determinant of that expectation value. Right? I mean, so the thing that you need to argue is that the expectation value of determinant of phi is non-zero. And it doesn't automatically follow from this. So, however, here, because phi itself was very big, And presumably
order
all
one.
fluctuations in determinant phi are order epsilon.
Yes.
That
So
can't
that was
change.
my statement. Yeah, that was my statement. Yes.
And just one more question about it. Sorry, I'm sorry to go interrupt, Gautam. Please, you continue first and then I'll
No. I think now I got it. So you're saying that there is just one, I can go to a gauge in which there is just one eigenvalue of phi 1, and similarly for phi 2 perhaps, which is there's a square root or trace of phi 1 dagger phi 1. Yeah. And then the determinant would be just that eigenvalue to the power n or something like that. And that's the, okay.
Yeah.
Plus order epsilon.
Plus order epsilon corrections. Yes.
Yeah. I have one follow-up question on that. Since the determinant is an operator that itself involves in, might it be that the fluctuations of that are actually not controlled by epsilon, but also are order 1, and so could wash out this order 1 thing? Because you really want to argue that there is a gauge invariant operator that is charged under your global symmetry that has non-zero. Yeah. That's really what you want to argue.
Yes.
Okay. And I'd like, just to be completely sure, the simplest such gauge invariant operator is this determinant. This is what you would really want to argue. So in the best world, what you would do is to compute the quantum effective action for this determinant. Like turning on sources for this determinant. That might be a very tough thing to do in practice. So now you've done something else, and I want to make sure that you can parametrically argue that what you've done implies that the quantum effective action for the 1-point function for this determinant itself has non-zero value. Now, had the operator been a small one that did not scale with n, I think what you've done would be clearly sufficient. Because you would have some order 1 thing and everything would be an order epsilon fluctuation. It couldn't change that order. But I'm a bit worried since your operator itself is big in the same parameter that is justifying your smallness.
No, that just brings out an overall scaling. In case of the CFT, that just means that...
You're probably right. I can't see it in my head.
No, I'm just saying that in case of the CFT, that would mean that you pull out an overall, you'll have an overall factor of t to the power n. Because see, for instance, if you look at this thing, look at the wave that phi I gets. So you have an overall factor. This is order 1. This is order n, right? So, and you have this has some, this thermal mass square has a t square in it. It's t square, it's some order lambda times t square. So the order lambda, the lambda piece just gets cancelled, right?
See, I'm not worried about computing the determinant on this expectation value. I'm worried.
No, I'm just saying that there's an overall t to the power n that just gets pulled out.
Okay.
So that's what happens, and then you have this.
I'm saying if you compute the expectation value of the determinant operator, that's not the same thing as plugging in some expectation value of these phi's into the determinant.
No.
There are fluctuations around that.
There are fluctuations.
Now, I would have expected, naively, you would say those fluctuations are order epsilon.
Yeah.
And therefore, if this what you get from just plugging in this stuff is order 1, the order epsilon fluctuations cannot wash that away.
Yeah.
My worry, which is probably unfounded, but just to pose it, is that because the operator itself has n in it.
Yes.
It could be that the fluctuations have, when you do the calculation, you find an extra factor of n. So the fluctuations are controlled not by epsilon, but by n times epsilon, and so on, of the same order as the classical wave. And then
so Shiraz, there is n here also. Are you taking that into account?
Which n?
Oh, you are, I guess.
In the phi 2. That there can be an additional power factor of n, so that it's n times epsilon. So, but then you can just here comes this question that how does one? What is the path? So.
No, sorry. I meant something else. The wave of phi 2 is n times order 1. You see, there is an n times order 1. While your argument, I thought, was doing n times epsilon, right? Or is it? Well, one has to be careful, I guess, in n counting.
So
but it could be n squared times epsilon.
A relative factor of n times epsilon, and then the whole perturbation theory just gets spoiled. So that's I think Shiraz's concern.
Yeah, that's at least intuitively my question. I can't see all the scalings in my head.
Yeah, so I'm not also completely sure of how the factor of n would go, because I've not. It's not very.
Yeah, it would be nice just to estimate what order these fluctuations are compared to the effect that you're keeping, just to make sure that it cannot wash it out.
Yeah. Okay. Yeah. So I have not done the computation, so I'm not completely sure of how what would be the factor of n in such subleading terms. But yeah, you're right that if there is some yeah.
I mean, this worry comes about only because the first non-trivial charged operator is itself a complicated operator. So you have to, I mean, I think it's probably not an issue, but just to raise the issue.
Yeah. Okay. So, but yeah, yeah, I have to think about it. Yeah, it's not very obvious. I mean, yeah, I agree with you. Yeah.
Okay, thank you. Yeah.
Okay. Yeah. Okay.
Okay. So if there are no further questions, let's thank Soumyadeep again for a very nice talk and answering all the questions. Nice.
It was very nice and very clear, Soumyadeep. Very, very nice talk. Thank you so much.
Okay.
Yes, absolutely. Thanks a lot.